Okay, so before the break, I was going to calculate, I told you that I was going to calculate the transfer functions from the two inputs we had from before to the new output I defined. Okay, so this is an example of choosing different signals in a system as outputs. I told you several times before that output of a system is not unique. So output depends on your purposes. And in this case, in addition to the speed of the car, we should better take a look at the gas pedal position to see what the controller is actually doing. So the controller is this box here. The input to the controller is the speed error. So the controller transfer function is just a constant number. So the controller, whatever the speed error is, multiplies that error with a constant number, and that becomes the output of the controller, which is the gas pedal position. Okay. So instead of the driver, the controller is actually stepping on the gas pedal, and this indicates how the control is performing. And to monitor that, we should define this as the output. So when this becomes our new output, to see what the output does, we need to calculate the transfer function from these two inputs to these are the two inputs to the new output, and we do that by using block diagram operations. Okay, so I did that quickly over the break. So this is my new output theta, and I was able to write it in terms of the two inputs VSSD and FD. And when I combine VSSD is a step signal with magnitude VD, and FD is also a step signal. So this is 1 over S. So finally, I can see what the gas pedal position does by finding the output corresponding to this transfer function. Okay. So I can normally do this by doing. If I want to do this manually, I need to do partial fraction expansion and then take the inverse transform through that. But obviously, it will take a lot of time. Instead, I'm going to use MATLAB to simulate this transfer function. And I did that as well in the break. Okay, so this is the transfer function. So whatever you see here is written here in MATLAB. And when I run this, the plot I'm going to get through this command will be the. So let me just write this. Anyway, it's going to show me the gas pedal history. Okay, so let me first start with the ideal case. Okay, so first I start with the smaller value of 0.1, and let me check. The engine parameter is the ideal parameter, and alpha is equal to 0. Okay, so this is the ideal case, and let me just run this code, and let's take a look at the gas pedal position. Okay, so this is the gas pedal position. So it starts from 0. Well, apparently it doesn't start from 0, but whenever we give the command, the controller steps on the gas, and then the gas pedal position reduces and it settles down at some value here. But when you look at the transient, you see that it reaches a value of 2.5. But obviously this is not acceptable, because if you remember how we defined theta, theta was normalized to be between 0 and 1. Okay, so 2.5 means that the controller will try to apply input which is greater than the applicable input. Okay, so this is the case for even k is equal to 0.1. So simulating the above transfer function in MATLAB gives the following results with for ideal case with k is equal to 0.1. Almış. The figure shows that for even this low value of k, the gas pedal position reaches a maximum of 2.5, which is impossible to implement. Theta was normalized to be between and 1. So this result shows that to implement this controller, we need an engine that is at least 2.5 times more powerful than the original engine. Okay? Okay, so now let's see what happens if we use k is equal to 1. So according to this table, k is equal to 1 is a very nice thing because it makes the performance very nice. But if I change the k number to 1, and run this code again, okay, so this is what I get. So 50 seconds is too long, so let me reduce the time to something. Instead of simulating system for 50 seconds, let me do it for just 5 seconds. For k is equal to 1, the peak gas pedal position is 25. So these results show that if we want to have a very nice controller, that can drive the car at the desired speed, under all disturbance, under all, oh yeah. We need a very powerful engine. Okay? Okay, so the message I was trying to give today is the following. So closed control is a very good thing. If you have a closed control, by choosing proper values, you can make the system as good as you want. Okay, so you can make the car able to reject all kinds of disturbances you can imagine. But in practice, it's not that easy. So even though in theory you can obtain very nice results, to be able to implement that control in practice, you need hardware that is powerful enough, the hardware that is good enough to support that controller, and in this case that corresponds to the engine. So if you can have a car that can produce incredible amount of force during transients, like consider this one, so it needs to give a lot of force in this region, then you'll be able to get those results. Okay, so that was the idea of the previous lecture, or the last week's lecture actually. Okay, any questions? Okay, let's see. So by the way, here I was just trying to make you understand the benefits of closed-loop control and the drawbacks of closed-loop control. So I think this example was good in that sense. But in practice, if you want to design a cruise controller for a car, you can do better than this. Okay, so this is the simplest controller. Instead of making a constant number, if you choose something dynamic, that means if you can make this something like a function of s, okay, so you can make better than that. So choosing this part, deciding what controller to use, is the job of a controls engineer. Okay. Okay, now I would like to show you something more fun. So closed control is actually everywhere. Every day in our lives, we actually use closed control without even knowing it. In fact, the simple act of walking is closed control. You can understand this when you watch a kid trying to walk for the first time. You know, walking is really a very difficult process, and a baby who is trying to take his first steps, he or she struggles a lot while doing that, because it's not easy to balance your body. And while doing that, we actually use closed control. We get feedback from our feet. So how we stand, we get information from our feet, and we balance our body accordingly. And while walking, we get feedback from our eyes to check the road ahead. Bunu siz de yaşamışsınızdır. Geçen yıl bir 5-10 sene önce bir güneş gözlüğü almıştım. Güneş gözlüğü birazcık daha bombeli bir camı var ve biraz yamultuyor. Yani düz yolu biraz daha kavisi gösteriyor. Bu inanılmaz afallattı beni. Yani bunu gözlük kullananlar herhalde daha iyi biliyordur. Yani ilk başta böyle ne oluyoruz falan oldu. Böyle merdivenlerde inerken böyle durup tane tane falan atıyordum adımlarımı düşmemek için, ya da gözlüğü çıkartıyordum. O şeyi aslında çok bariz yapıyor. Demek ki gözden biz aslında bilgi alıyoruz. Yani göz olmasa öyle laylardan yürümesi o kadar kolay bir iş değil. And not just vision. Obviously, vision is a very important part of walking, but the feedback we get from our feet is also very important. So that's why it is not easy to make robots that can walk like people. I don't know if you know if you knew that or not, but trying to make a walking robot with 2 feet is not an easy thing, because we use feedback from our feet, and without that, it's not easy to walk. Okay, so I have this demo I like doing in class, and I have this long pen, and I want to use this as a balancing stick. Okay, so I will try to keep this upright by moving my hand. So obviously when I just leave it, it just falls down, right? And I can make this keep upright if I control my finger accordingly. So I guess I need to stand up. Bunu yaparken ders 3 kere bu geriye düştü, o yüzden dersen. Okay, so as you can see, I can control this, right? This is a control problem. And in fact, it's a feedback control problem. Because I'm checking the output of the system with my eye. So that means I can not possibly keep this upright without looking at it. It's not really possible. So this shows that feedback control is essential for this problem. It is not possible to control this without applying feedback control. Videoda bakanlar geri kalmasınlar. So this is what I was doing. And if I try to do the same thing with my eyes closed, results not as good. Bayağı iyi yaptım aslında. But the message I'm trying to give here is so this part of the loop is essential for certain systems. So this is the feedback loop, and in the so let me go back to the lecture notes. Okay, so this is the block diagram for the demonstration I just made. Okay, so this is the control. It's a very simplified view of the control problem. So this is my system, and the position of the stick is the output. Let me call that theta. The input is the force I apply to it with my finger. And this is the block diagram. Okay, so the control is actually my brain. Okay, so I decide how to move my finger. So this is the controller. My hand is my actuator. I use my hand to actually implement that force. So this is the system itself. And the feedback loop is closed with my eyes. Well, in fact, I get a little bit of feedback from my finger as well. So that's why I was able to hold it for some time even when my eyes were closed. But if I try to do this with this, for example, Seferinde bu çubuk var, düştü şuradaki boşluğa. Ama derste öyle bir heyecanlı geldi ki anlattım, şimdi bak süper olacak, çok eğlenceli şeyler göstereceğim falan diye küt diye ders öyle şey düşünce daha ilk denememde. Ne yapacağımı bilemedim tabii. Bütün dersi onun üzerine kurgulamışım. Bir de 2 saat dersin en başında oluyor bu. Öyle kaldım. Neyse düşünüyorum nasıl yapsak falan diye. Sonunda şeye karar verdim. Gideyim yenisini yapayım bari dedim şu çubuğun. Ofise gittim. Orada sınıf bütün sıraları falan çekmiş. Bu şeyi boşaltmışlar. Aldılar. Sonunda yaptık gene ama okay, so what's special about this stick is, well, there's something special about it, by the way. So this is something similar to this, right? And let me try to do the same thing with this one. This is much harder. So I cannot really keep this for too long. But for this, if I try hard enough, I can make this stay up upright for as long as I want. I can keep this for minutes. But it is really impossible for me to hold this one that long upright. So can you think why this is so much difficult than this one? Şurada da yapayım da. Okay, so this is the easy one. I can make this, control this for a very long time. Whereas this one is a lot more difficult to hold. Okay. Well, so this is what happens when I try to give too many messages at the same time. Well, what makes the control of the shorter one much more difficult than the other one is this one has very fast dynamics compared to this one. Okay, so we can see that by taking a look at the initial condition responses of these two systems. Okay, so I'm going to show you the responses, the initial conditions for these two sticks. Okay, so let's remember the system. Okay, so the theta is my output. I'm going to release the system from some initial condition, and then let's see how they move. Okay, I'm just going to, I will try to release them at the same time. I don't know if you saw that, but this one fell a lot faster than the other one. Okay, so in fact I can show you. So I'm going to show you the same thing on a video I recorded previously. Okay, I recorded this video in class before coming to the lecture. Okay, so this is where I release it. Okay, so I just release it here. And after a few frames, you see that the board marker is going down much faster. See, it's already on the floor, whereas the long one has still a long way to go. So this shows that to be able to control the short one, I need faster controller. Okay. Since this is a faster system, this can only be controlled with an overall faster controller. This requires everything in the loop to be faster. So if I go back to the block diagram, my hands need to be faster, my reflexes need to be faster, my brain needs to work faster. So if I can, which can be done by this. So if I study long enough, I can make, I can get used to controlling this fast one. But the reason why I get it's difficult to control the shorter one is because this system is faster. Ya bir sürü bir şey açınca bilgisayar bayağı bir zorlandı. Neyse bunu da tahtada şey yapayım. Aslında so that trying to control the stick is very similar to this problem. So you try to control the position of a missile by changing these control surfaces. So the control surface is similar to my finger, trying to control it. So the same problem, same thing applies here. If you want to control a missile, then your control needs to be fast enough to be able to handle that. So if you consider two missile systems with such different bodies, then as you can imagine, controlling this one requires a lot faster controller. Yani bu mesela şey olsun, böyle uzun menzilli bir füze olsun, değil mi? 300-500 kilometre gidecek füze. Ve bunun boyutları 5-10 metre merkezinde olabilir. Dolayısıyla bunun kontrolü nispeten kolay. Yani şuradaki kanatçıkları daha yavaş hareket etmek o sistem kontrol edilebiliyor. Ama şunda mesela küçük bir roket düşünün, işte omuzdan atılan, işte havadan uçlayan uçağa karşı. Onun çok daha hızlı kontrol şeyine sahip olması lazım. Yani buradaki kanatçıkları mesela her şeyin çok daha hızlı hareket edebiliyor olması lazım ki o kontrol edilebilsin.
Nereye gidiyor? Daha hızlı olması, sistem çekme neyi değiştiriyor? Yani etkisini nerede görüyoruz? Sabit tamam bunu söyleyebiliyorum ama formülde neyi değiştiriyor? Yani daha hızlı olması demek ne demek o formülden?
Böyle o kadar şaklavanlık yaptık. Videolarda gidecek herhalde. Bilgisayar kilitlenmiş görünüyor. O neyi etkiliyor? Şimdi o şeyleri yazdığın zaman onların arasında görmesi çok kolay olacak. Yani şurada blok diagramını çizersen bunu, şimdi orada hepsinin bir bloğu var. Değil mi? Mesela bu çubuğun kendi bloğu var. İşte ondan sonra işte elim vesaire. Onların hepsini şeyleri koyduğunuz zaman toplamda sistemin transfer fonksiyonu çıkardığınız zaman onların hepsini görebiliyorsun. Yani işte şu çubuğu çıkartıp kısa bir çubuk koyduğum zaman orada transfer fonksiyonunda onun ilgili kısımlar değişmiş olacak blok diagramda. Ve sen elimin kontrolcüsünü mesela oraya koyduğun zaman onu kontrol edemeyeceğini çok rahat görebiliyorsun. Oradan şey de ortaya çıkıyor. Senin sistemin böyle hızlandıysa kontrolcü yapabilmek için, kontrolü sağlayabilmek için kontrolcünün nasıl değişmesi gerektiğini de oradan çok rahat görebiliyorsun. Aslında yani o blok diagram işlemleri vesaireleri, yani bu tip şeyler hep kritik bir şeye sahip, öneme sahip. Oldu galiba ya. Okay, so we have about 10 minutes left, and I would like to draw your attention to another important detail which I didn't mention before. Okay, so when we obtained the unit step or step input response of the system, I showed you this result, and the transient response was plotted in terms of time constant, right? So we define the time constant, and this time constant determines how fast the system moves. And this time constant was defined as this for that problem, mass over that B coefficient. And I really didn't spend too much time on that. So, but this is in fact a very important parameter, obviously, because it totally determines how fast the system moves. So, for example, if you go back to these two, so what's different between the two is this has a much shorter time constant because this completes its motion a lot quicker than this one. So time constant is a very important property of a system. And for this system, it was m over b. Tau was defined as m over b. But where that comes from is the following. It comes from the transfer function of the system. Okay, so the transfer function of the car was 1 over ms plus b. And this has a pole, right? So the car transfer function was 1 over ms plus b, and there's a pole, and that pole can be found by equating that to 0 minus b over m, and this is equal to minus 1 over tau, right? Since tau was defined as m over b. Okay? So where the pole of the system determines how fast that system moves. So this is a very, very important result. So I should write this down. Is the inverse of the pole location on the real axis. And this number determines how fast the system behaves. So in the open loop case, the time constant doesn't change. The time constant is at m over b, but in the closed loop system, so far we only considered the steady state output of the car to check the performance. Another very important parameter in performance is the time constant. And in closed loop control, time constant of the system changes as well. So where do we see that? So it is actually the pole of the transfer function of the system, right? So the pole of this thing is the time constant comes from there. In other words, onun da daha güzel bir hali vardı ama. you simplify the above transfer function by inserting etc., what we get is so there should be somewhere here. Let me see. Okay, so if you look at the denominator, it has ms plus d plus k times ke. So the time constant is in the open loop case there was no k and the time constant was simply m over b, but in the closed loop case it is m over b plus this thing, and this thing is related with the controller. So the controller can change the time constant of the system as well. So in open loop tau was equal to what? It was 4 seconds, right? So let me just make sure that it is. It is 4 seconds. In closed loop with k is equal to 0.1, tau is plus 0.1 times, this is the ke value, 0.67. And if you use k is equal to 1, so the controller not only changes the steady state performance, but it also changes the transient performance by changing the time constant of the system. Okay? In fact, it changes a lot, right? So from 4 seconds, it goes down to less than a second. So that's a very huge difference. So let's see the effect of that here. So it's 0.1 here anyway. So what you see here is the responses with open loop and closed loop controllers. This purple one shows the response with open loop control. You see the effect of the time constant. It takes some time before it reaches the steady state. But with closed loop control, the steady state is reached a lot quicker. How fast it reaches is totally related with the time constant. Okay. Okay, so we are already out of time, so let me stop the recording.